Welcome to this lecture on research methodology. Today, we are diving into a fundamental topic for any zoology student or future scientist: the critical difference between an observation and a fact. While we often use these words interchangeably in daily life, in science, they mean very different things. Understanding this distinction is the very first step in conducting rigorous, meaningful research. Let us begin our journey into how we uncover the truth about the natural world. To understand what an observation is, imagine you are a detective walking into a room with a broken window. You see glass on the floor, a baseball nearby, and muddy footprints leading away. At this moment, you do not know the whole story. These things you see, touch, and measure are your observations. You are simply gathering the raw pieces of the puzzle. In research, an observation is exactly this. It is the raw, unfiltered data you collect from the world, using your senses or scientific instruments. It is the starting point of all scientific inquiry. Now that we have our detective analogy, let us look at the strict academic definitions. An observation is the systematic, purposeful, and objective gathering of data. It is not just casually looking around, it is planned. But what happens when multiple detectives look at that same baseball and all agree it is a standard baseball? That shared, undeniable piece of reality becomes a fact. A fact is simply an observation that has been confirmed so many times by so many independent people that we can safely treat it as true. In science, facts are empirically verifiable, though they can be updated if better observations emerge. This brings us to an important question. Why do we care so deeply about this distinction? The answer lies in human nature. We are naturally biased, and our personal observations can easily be flawed, subjective, or misinterpreted. For instance, if a researcher sees a plant grow faster in sunlight, that is just a single observation. It is not yet a scientific fact. It only becomes a fact when the experiment is repeated globally, controlling for variables like soil and water, and yields the exact same result. Without this rigorous process, our research would be filled with personal opinions and illusions. Now that we understand the conceptual difference, let us look at how researchers handle this mathematically. To understand how a raw observation relates to a true fact, researchers use a mathematical model called classical test theory. This model explains a fundamental rule of research. Every single observation we make is a combination of two things. First, the actual truth, which is the fact we are trying to find. Second, some level of measurement error. Because our instruments and senses are never perfect, error is always present, and it pushes our raw observation further away from the true underlying fact. This concept is represented by a very simple but powerful equation. X equals T plus E. Let us break down where this comes from and what each symbol means. The symbol X represents the observed value, which is the raw data point you just measured in your experiment. The symbol T represents the true score, which is the actual underlying fact or reality you are trying to discover. Finally, the symbol E represents the error. This includes any mistakes, biases, or instrument inaccuracies that happened during your observation. Physically, if the error E increases, our observation X moves further away from the true fact T. This formula tells us in plain English that what we observe is never perfectly equal to the truth. Before we move on, let us see this with a concrete example. A psychologist observes a subject's reaction time as 250 milliseconds. This is our X. The computer has a known error margin of plus or minus 50 milliseconds. We are asked to find the range of the true factual reaction time. We choose the observation equation because it links our knowns to the unknown truth. By rearranging the formula to t equals x minus e, we can plug in our negative and positive error bounds. Subtracting negative 50 gives a maximum of 300, and subtracting positive 50 gives a minimum of 200. Physically, this final answer means the true reaction time is trapped within this window, showing why a single observation is not yet a precise fact. Now that we have used the basic formula, let us understand where the next concept comes from. This chunk of our proof is setting out to establish how variance works across multiple observations. We start with our fundamental axiom: x equals t plus e. In statistics, if the true score and the random error are independent of each other, the variance of their sum is exactly equal to the sum of their individual variances. This mathematical reasoning gives us our next step. Total variance equals true variance plus error variance. By simply rearranging this equation, we prove that true variance is the total observed variance minus the error variance. This intuition is crucial. We are mathematically stripping away the noise to find the truth. This derived variance leads us directly to the reliability coefficient. Conceptually, this formula calculates what percentage of our observations is made up of solid truth rather than random noise. Let us define the symbols. R stands for the reliability coefficient, which is a ratio that always ranges from 0 to 1. The symbol sigma squared sub t represents the variance of the true scores, meaning how much the actual facts vary. The symbol sigma squared sub x represents the total variance of the observed scores. Physically, if the true variance increases while error stays low, R gets closer to 1. This means our observations are highly accurate and can confidently be treated as scientific facts. Let us apply this new formula to a medical scenario. A researcher observes patient heart rates to establish a baseline. We are given that the total variance in the observed heart rates is 50. We are also given that the variance caused by measurement error is 10. We are asked to find the reliability of these observations. We choose our derived variance formula first, subtracting the error of 10 from the total of 50 to find a true variance of 40. Then we divide this true variance by the total variance of 50. The mathematical result is 0.80. Physically, this final answer means that 80% of the observed data represents the true factual state, which is considered strong enough to establish a fact. So, we have successfully calculated reliability. This brings us to the final result of our proof arc, where we establish exactly why a reliability of 1 represents a perfect fact. We start with our reliability definition. In the denominator, we substitute the total variance with true variance plus error variance, which we proved earlier. Now, look at the mathematical reasoning. What happens as our measurement error approaches 0? The error term vanishes, leaving true variance divided by true variance. The ratio perfectly equals 1. The intuition behind why this works is beautiful. When you completely eliminate measurement error, your raw observation becomes identical to the underlying reality. You have successfully turned an observation into an undeniable scientific fact. This brings us to a visual summary of everything we have discussed and proven. Look at the diagram on your screen. On the left, we start with the raw observation, labeled X. This is our starting point, filled with uncertainty. The arrow guides us through the critical middle step, repeated verification and error reduction. This is where the rigorous work of research methodology happens. Finally, we arrive at the scientific fact, labeled T on the right. Notice the large arrow at the bottom? It shows that as we move from observation to fact, we are moving from a state of high error to low error. The diagram teaches us that a fact is simply an observation that has survived the rigorous stripping away of error. We have reached the end of our topic, so let us reinforce the most important ideas. First, remember that observations are just the raw, unfiltered data points we collect, and they always contain some degree of error. Second, facts are the verified, undeniable truths that emerge only after those observations are rigorously repeated and tested. Third, classical test theory gives us the mathematical framework for this, showing that every observation is a mix of truth and error. By systematically reducing that measurement error, we strip away the noise and reveal reality. Mastering this distinction is the most fundamental skill you will develop in research methodology. Great job following along, and keep questioning what you observe.